Okay, the last portion of this lesson is going to be over arc length, Euler's method, and logistical growth. Okay, your formula for arc length is going to be the integral from a to b of the square root of 1 plus the derivative squared. If it's given as x is equal to, then you'd have y limits. If it's given as y equals 2, you have x limits. And then you have the parametric form, where it's dealing with t's, where you have an x equation and a y equation. This would also be the formula for total distance traveled if you're in parametric form. Okay, so find the length of the curve from 1 to 2, integrate in the calculator. So we're going to start off by finding dy dx. Derivative natural log is 1 over x. So the length of the curve is going to be the integral from 1 to 2, the square root of 1 plus 1 over x quantity squared, like that. We're going to put that in the calculator. Math 9 it. So we go to y equals, and I'm going to put 1 plus 1 over x squared, like that. And y equals, and I'm going to quit. I'm going to math 9. Wait, did I put the square root? Let's go ahead and put the square root in there. Gosh darn it. So we're going to put the square root in there. Okay, math 9, 1, comma x, comma 1, comma 2. And you get 1.222. Okay, easy as that. Find the length of the curve for y equals x to the 4th from 1 to 5. So dy dx is going to be 4x cubed. And we're going to follow our formula. Put your limits. Square root of 1 plus 4x cubed squared dx. And then we're going to do the same exact thing we just did. Let's just change this to 4x. 4x cubed under the square root. Quit. We're going to math 9 it. We're going to go from 1 to 5. So we get 624.0597. Okay. And the last one, we're in parametric form. So we got an x and a y. So we're going to find dx dt. The derivative sign is cosine of t cubed. And then we chain rule it. It's 3t squared. dy dt is going to be 5e to the 5t. Okay, so your arc length is going to be the integral from 0 to pi, square root of 3t squared cosine of t cubed squared plus 5e to the 5t. Okay, dt, we gotta square it. Okay, so what I'm going to do is I'm going to put my dx dt in y1. So 3x squared cosine of x to the 3rd. So t is going to function the same thing as x. Okay, when we integrate 5e to the 5x. And let's go ahead and square it. There's different ways you can put this in there. Whatever way you choose is fine with me. Okay, so we do math 9. We're going to square root y1 plus y2, like that, comma x, comma 0, comma pi. This might take a second. I got 6.64 times 10 to the 6th power, so it's a large number. Most of these questions came from multiple choice, where it said you didn't have to evaluate it, just said set up the integral. So Anyways, we know how to do that. Just want to practice putting in the calculator. Okay, Euler's method. We covered Euler's method a few lessons ago. Euler's method follows this formula right here. Y naught is going to be your initial y value. H is going to be your step size, and f of 0, so f is going to be your derivative. So plug it into the derivative. Okay, so we're going to start with our formula. It says, given that y of 1 is equal to a -3, derivative is 2x plus y, we want to approximate y of 2 using Euler's method. Okay, your step size is going to be 0.5, and we're starting at x is equal to 1. So our formula starts out like this. Our initial y value is a -3, our step size is 0.5, and f naught is plugging into the derivative. So we're going to plug in a 1 here and a -3 for y. So you should get a -1. Okay. So 0.5 times a -1, and then add the -3 to it, you get a -3.5. So this leaves us at the point 1.5, -3.5. Okay, now we're going to repeat the process. Okay, so y1 is the previous y value, so it's -3.5. Your step size is still 0.5. And f of 1, we're going to plug this point right here into the derivative. So 2 times 1.5 is 3 minus 3.5 should give you a -0.5. So y2 comes out to be -3.75. This comes out to be -0.25 in combined or like terms. So this would put us at the point 2, -3.75. Oh, 3.75. So your answer is 3.75. Okay. Now, this is the same thing, but it gives you a table of derivatives instead of giving you a function. Okay, so the table shows values of the derivative of the function for selected values of x. F of -0.2 is equal to 1, which is the approximation for f of 0.4. And we're going to use a step size of 0.2. And we're going to start at x is equal to -0.2, which is the first point. Okay, so y1 is equal to y naught plus hf naught. y1 is equal to 1 plus your step size is 0.2. Your initial derivative is 0.8. And so putting that in the calculator is 1.16. So that leaves us at the point 0, 1.16. Okay, so every time you do your point, you're stepping up your step size. Okay, y2 is equal to y1 plus hf1. y1 is 1.16. Your step size is 0.2. And then your derivative at that point is 1.2. Putting that in the calculator, you should get 1.40. So that leaves us at the point 0.2, 1.40. And let's do it one more time. hf2. So y2 comes out to be 1.40. Your h is 0.2. And your derivative value is 1.7. Put that in the calculator. You should get 1.74. So this puts us at the point 0.4, 1.74. And this would be a calculator question. They don't expect you to do this by hand. It's very possible that this would show up on free response for 2020 this year because it involves some sort of table. And on your homework, we're gonna, I included some free response that deals with this at some point. Okay, this is something we haven't talked about in the semester. It's just really not worth spending a lot of time on because it usually shows up on one question on multiple choice. So we know that exponential growth looks like this. Logistical growth is it grows and then it reaches a carrying capacity. Okay, it lines out to a certain population. So a logistical model follows this right here. dP dt is equal to RP times 1 minus P over K. Where R is your growth rate, P is your population, and K is the saturation level or carrying capacity. Identifying this K is super important on multiple choice questions, okay? So pretty much it's the limit as your time goes to infinity is what the carrying capacity is. Okay, so first example, it says the number of moose in a national park is modeled by the function m that satisfies the logistical differential equation dm dt is equal to 0.6 m times 1 minus m over 200, where t is the time in years. And the initial moose population is 50. What is the limit as t approaches infinity of m of t? Okay, so what this is asking for is the carrying capacity. Okay, so from our logistical model, we can see that K is the carrying capacity right here. So your answer is 200. And that's it, there's nothing more to it. Next one, the rate of change of the number of people on an ocean beach is modeled by a logistical differential equation. Okay, so let's go ahead and write that. Okay, so it says the maximum number of people allowed on the beach is 1,200. So that's going to be your carrying capacity. At 10 a.m., the number of people on the beach is 200 and is increasing at a rate of 400 people per hour. So this is going to be your population is 200 and your dP/dt is 400. Okay, write a logistical model. So just like when we did PERT, you got to find your R first. So 400 is equal to R. Your population is 200. 1 minus 200. Your carrying capacity is 1,200. I'm going to solve for R. So R comes out to be 12 over 5. Okay, so if I want to write my differential equation model for this, it's dP dt is equal to 12/5 P times 1 minus P over 1,200. Now, a lot of times it's not going to show up like this in this form. So what they do is they get a common denominator and they do around the world right here. So they would do dP dt is equal to 12/5 P times 1,200 minus P all over 1,200. And what they do is they pull this 1,200 out here. So a lot of times the way it would read is this 12/5 times 1,200 comes out to be 1 over 500. So it would take this form. So you could identify your carrying capacity as 1,200 from this. So either one of these is correct, but a lot of times on multiple choice, it's going to look like this. Okay, so that has been Euler's Method, Logistical Growth, and Arc Length. So hopefully you have a good night. And if you have any questions, feel free to reach out. Thanks. Bye.